Okay, hello Math 182 students. So what I'm doing here is I'm making just a fresh recording of the example that we looked at yesterday in class. So you have this copied in your notes already, but remember we have a sphere with radius 1 meter that has temperature 15 degrees Celsius, and it lies in a concentric sphere with radius 2 meters and temperature 25 degrees. The temperature function, T, is a function of R. Okay, they're treating the temperature function as a function of R. And the temperature function at a distance R from the common center of spheres satisfies this differential equation. Okay, now this is a second order differential equation because the derivative, because of this right here. This is a second derivative of T with respect to R. So when you learned about the technique of separable variables, you worked with first order differential equations and were able to solve explicitly for the solutions using the separation of variables technique. But in this problem, because you have a second derivative in the differential equation, you have to make a substitution to convert this second order differential equation to a first order differential equation. And so the substitution that you're going to make is you're going to let S be the derivative of T with respect to R. Okay, and you'll be able to convert then this second order differential equation into a first order differential equation and eventually solve for your temperature function as a function of radius. So I'll go to the solution here, which I've outlined before, but let me just go through it here. So here is the second order differential equation, right? There it is. And we're doing the substitution. We're letting S equals dt dr. And when we do that, the differential equation becomes here's where the substitution is, right here on this step here. So remember I'll make a comment here. The second derivative of T with respect to R is equivalent to taking the first derivative of T with respect to R and differentiating that derivative with respect to R. That's Leibniz notation. So, well, dt dr, of course, is equal to S. dt dr equals S, right? And so we can convert then this second order differential equation to this first order differential equation right here. Let me do that a little bit cleaner. Yeah, we take the second order differential equation, and by virtue of this substitution, the second order differential equation becomes this first order differential equation, where now the dependent variable is S, not T. Okay? So we go forward and separate the variables. Okay, so these are common steps that you've seen before. And then we need to integrate this equation. We need to get the antiderivatives. Well, we are going to be assuming that it makes sense that the radius, of course, is greater than 0. And also, it will also make sense that, hold on here. It'll also make sense that, hold on, that S is greater than 0. So in other words, we're assuming dt dr, okay, is greater than 0 because that's what S was defined as in our substitution. So we're saying that as radius increases, the temperature goes up, which in this application is reasonable. Okay? So when we do the antiderivatives, here, okay, the antiderivative of 1 over s, okay, well, what is the antiderivative like of 1 over x? Okay, that's equal to the log of the absolute value of x, right, plus some constant. However, we're assuming that s is greater than 0. So the antiderivative of 1 over s would just be the log of s. And similarly, since we're assuming that the radius is greater than 0, the antiderivative of 1 over r would just be the log of r without the absolute. You don't need to have the absolute value on the r because we're assuming r is positive. So now what we do then, of course, is we have to go ahead and solve for s here. Okay, we want to solve for s in this equation. So we have to exponentiate both sides of the equation, which we do. And then remember the log. So how do we get then to this step here? Well, the log of a to the bth power is equal to b times the log of a, right? So if we have -2 times the log of r, okay, then that's going to equal the log of r to the -2nd power, okay, by this rule here. And so this is how we get the log of r to the -2nd power here. And when we exponentiate that, we're going to get r squared, r to the -2nd. Okay, and then e to the c is just k. And so s will equal then k over r squared. That's what s will equal. But now what we're going to do, we're not interested in finding out the solution for s. We're interested in what's the solution for the temperature. So what I can do is, now that I have solved for s, I can substitute back in for s the dt dr. And then I can proceed forward to doing my separation of variables. So if you need to slow the video down, the recording down, you can do that. But I'm just sort of moving through here. Okay, so now here is our equation to solve. That's fine. So we get the antiderivatives. Antiderivative of 1 is t. Antiderivative of r to the -2nd is -r to the -1st power. And then, of course, we have a constant of integration, which I'll call a. Okay, now I could call that like C3 or whatever, but I'm just going to call it a. So it turns out then that t will equal -k over r plus a. So we have our temperature, we have now temperature function. Okay, we have the temperature function, but of course, in order to use the temperature function, we need to figure out what those constants k and a are. Okay, I mean, this is a general solution, but in order to answer the question, well, we need to find an expression for the temperature subject to the initial conditions. We need to solve for k and a. Well, we're told back in the problem that when the radius is 1 meter, the temperature is 15 degrees. So that means then we can, that means we can apply the initial condition, plug it in the equation here, and when we do so, we'll end up getting that t equals -k over r plus 15 plus k. In other words, a equals 15 plus k. So now our temperature function is -k over r plus 15 plus k. But now we want to solve for k. Well, we were given a second initial condition that if we go back to the problem, We were also given that when the radius is 2 meters, the temperature of that sphere is 25 degrees. So then now what we can do is apply this initial condition, substitute it in this equation here, and when we do so, we'll get 10 equals k over 2, which means k is 20. Okay, and so if I go to the next page, k is 20. Now a equals 35, and why is a equal to 35? Well, remember from the previous page that a is equal to 15 plus k. So if k is 20, then a equals 35. And so therefore, our temperature function equals negative 20 over r plus 35. Okay, and that's our answer. Okay, so I hope this was helpful, and thank you very much.